So now let's go on to talk about the third time we use bell curves. So the third time we use bell curves is this idea called a normal approximation to a binomial probability distribution. So let me motivate this with an example. So let's start with an example. So let's say that you flip a fair coin 100 times. So let's first look at the probability distribution for this situation. So let's say that we were to plot this distribution where the x-axis represents the number of heads that we end up observing out of each of the 100 flips. So number of heads observed from 100 flips. And let's say that on the x-axis we label all the possible values of this variable. So all the possible values coming from the number of heads observed from 100 flips. So what are all those possible values?
1 or 0 to 100.
0 through 100, very good. So you can't observe a negative number of heads if you flip a coin 100 times. And you can't observe more than 100 heads if you flip a coin only 100 times. So it's anywhere from 0 through 100 here. And for each one, we're going to have a bar with a certain height that reflects the probability of that variable taking on each of the values on the x-axis. If you flip a fair coin 100 times, how many heads should you expect to observe with the greatest likelihood?
50.
Yeah, 50. Good. Because it's a fair coin. So we have a bar with a certain height representing the probability of observing that number of heads when you flip a fair coin 100 times. Now, if the coin is fair, should you expect to observe 50 heads every time you flip the fair coin 100 times? No, so you very well could observe 51 heads for a fair coin out of 100 flips. So 51 is going to be here, but the probability or the height of this bar is going to be a little bit lower than what it was before. And as you move away from 50 heads in either direction for 100 flips of a fair coin, you're going to get, the probability will get less and less that you actually observe that many heads out of 100 flips. So this is what the distribution representing the number of heads observed out of flipping a fair coin 100 times looks like. So, how would you calculate each of these individual probabilities? For example, if you wanted to find the probability of, let's say, 55 heads out of 100 flips, that probability would represent the height of this bar. So how would you find the height of this bar, or the probability of getting 55 heads out of 100 flips? I'm going to this. So you guys happen to remember? Okay, so if you want 55 heads, because it's a fair coin, the probability of heads is 1/2. That means you want one coin to be heads and another coin to be heads and another flip to be heads and so forth. So you can multiply 1/2 by itself 55 times. Is that the final answer?
No.
Okay, so what's missing?
You have to do the probability that it's not heads, and you have to do the 100 choose 55.
Okay, good, yeah.
Why is it 1/2?
Yeah, because it's a fair coin. So the probability of heads, because we want 55 heads, is gonna be, probability of heads will be 1/2, because we're told that the coin is fair. And so because we want 55 heads, we're gonna multiply by that probability of heads 55 times. Just like you said, we can't just stop there, because 55 heads implies in the situation that we also must have 45 tails as well, if we were to have 55 heads in 100 flips. So we must have 45 tails. So now we have to multiply by the probability of tails. But because the coin is fair, the probability of tails is also 1/2. So then we multiply by another 1/2, 45 times. So that's the same as raising it to the 45th power. But there's not just this one way of getting 55 heads and the remaining 45 tails. There's lots of ways to get 45 heads out of 100 flips. So now we have to have a counting component where we take all those different ways into consideration. And so now we have 100 choose 55. And this is the binomial probability formula. So go ahead and punch this in and let us know what number you get that represents this probability. Yeah.
0.048.
Yeah, 0.048. Give me maybe a few more decimal places.
474.
0.04.
474.
74, okay.
It was still 8. It
Oh,
was just after
still
8, 74.
8, and then 474.
Yes.
Okay. Okay, so this is the exact probability of getting 55 heads out of 100 flips. Or in this picture, it's the actual height of this bar at 55 that represents the probability of getting 55 heads out of 100 flips. So this is how you get this particular probability of 55 heads. How would you get the remaining probabilities or the remaining heights of the bars? How would you find the height of the remaining bars?
Same way you found that one.
Same way, use the same binomial probability formula. Just different number of successes here. But same formula applied. So if we have this probability distribution and all the probabilities or heights of the bars are calculated using the binomial probability formula, then what do we call this particular probability distribution? What special probability distribution is this? Well, it can be approximated with a bell curve, but the actual distribution is, that's a property, it's metric. But the actual distribution of this probability distribution is a binomial probability distribution. So if you have a probability distribution and each of the probabilities or all of the probabilities are binomial probabilities, then this whole probability distribution is a special case called a binomial probability distribution. So that's what this original probability distribution in black is. Because all these probabilities are binomial probabilities, the distribution is a special case called the binomial probability distribution. But as there was one observation, this can actually be approximated. The shape looks like it's the shape of a what?
Bell curve.
Yeah, a bell curve. So you can actually approximate this with a bell curve, even though technically it's not a bell curve. And the reason why it's not actually a bell curve is that the bell curve is this blue distribution that is continuous, that doesn't have any gaps in it. But the original distribution is this black distribution that has all these gaps in between. So why does the original distribution have the gaps in it? It's discrete, very good, it's discrete, and the reason it's discrete is you can't have the probability of fractions of coin flips. So you can only have 50 heads out of 100 flips, or 51 heads, you can't have 50.8 heads. And that's why anywhere in between these whole numbers have probabilities that are zeros, and that's why you have these gaps. So the actual distribution is the one with the gaps in black, called the binomial probability distribution. But the approximation is the one in blue, and we call this the normal approximation to the binomial probability distribution. Okay, so we have two distributions here. One is the actual distribution in black, and the blue one is just the approximation to the original. All right, and so if we wanted to find the probability of 55 heads out of 100 flips, we know that visually that corresponds to finding the height of this bar at 55. And we can find the height of that bar by using this formula. And so we know that because we can approximate this original distribution in black with this blue distribution instead, now let's talk about how we can use the blue distribution to maybe try to get the same answer that we got before. So if we want the probability of 55 heads, for example, if we use the blue distribution now, remember the blue distribution is not continuous. And the way that we find probabilities of the continuous distributions is we can't add up heights of individual bars anymore because there are no individual bars. We have to now find areas of regions. And so if we wanted to find the probability of exactly 55 heads using the bell curve, we said mathematically the probability of 55, but using this blue bell curve, what's the probability of an exact number under a bell curve? Yeah, it's 0 because we're finding area instead. So the area of this one line under the bell curve is 0 because there's no space inside the line. So this probability ends up being 0. And obviously this is not the same answer. But the reason it's not the same is because this 55, we're treating it as a single data point. But if we want to approximate this answer, in real life, when we say 55, we actually are given it a tolerance between two numbers. So in real life, we are adding and subtracting a tolerance of 0.5 in either direction, based on how we round numbers. So 55 is really the same as the numbers between 54.5 and 55.5. And now if we give the number 55 a region that we can find the probability, that we can find the area under the bell curve for, then we can use this area to represent the probability. So instead of finding the probability of 55 by finding the area of a single data point, which we know for a continuous distribution is 0, now we give that single data point a region around it, so that we can find the area of that region to represent that probability. So, given this bell curve, and to find the area of this region under the bell curve, how do we find this area? Based on what we've talked about before. Yeah, find z-scores. So basically, we have these two boundaries here of 54.5 and 55.5, and we want to find the area between those by finding the z-scores of each of them. Then we'll look up the left areas and we'll subtract the left areas. Okay, so now let's go ahead and find the z-scores here. So, again, to remind you of what we're doing here, to remind you of the big picture, we've already found the exact answer of the probability of 55 by finding the height of this bar. But now we want to approximate that answer by finding the area around this data point of 55 using this new blue bell curve instead. And to do that, we're now going to find the z-scores of each of these boundary values around 55. So the z-score of 55.5 is going to be this data point minus the mean, divided by the standard deviation. So now what we need is to know the mean of the standard deviation in order to find the z-score. So what is the mean of this distribution? Yeah, so we happen to know it's 50 because we knew that the peak of this distribution occurs at 50 heads for a fair coin if we flip it 100 times. So we know the mean is 50. There's also a way to calculate that 50 if we didn't have that intuition to get the 50 in the first place. So how would we have calculated the 50 to find the mean?
Divide the sample size by, oh, I lost my train of thought.
Okay.
Add them all together and divide by the amount you did.
Okay, so we have a binomial probability distribution here. So recall that if we have the special case of a probability distribution, then there's a shortcut to find the mean of standard deviation. Do you guys remember what the shortcut is?
It's square root of the total multiplied by probability multiplied by the, what's the word?
Okay.
Complement of the probability?
Okay, good, good. So if we have the special case of a binomial probability distribution, then the mean turns out to be n times p. And if you look at this example, n is the total number of trials or flips, so what's n in this case? N is 100, and p is the probability of success per trial or per coin flip. But we have a fair coin here, so the probability of success or heads is 1/2. So this will be 1/2. So 100 times 1/2, that's the 50. And that's the same mean, or 50, that we're expecting here. So the mean turns out to be 50. And the standard deviation also has a shortcut formula, and that ends up being,
Square root of n times p times q.
Okay,
which is
great.
complement.
great. So it's the square root of n times p times q, so where q is the complement of p. So this ends up being n, which is 100, times p, where p is the probability of heads for this fair coin, that's 1/2, or 0.5, and q is the probability of tails for this fair coin, that turns out to also be 0.5. Yeah, so if you evaluate this, you'll see it's the square root of 25, which is 5. So the standard deviation turns out to be 5. So the z-score of this data point at 55.5 ends up being 55.5 minus 50, or 5.5, and then the standard deviation is 5. So that simplifies to give 1.1. So that's the z-score of this right boundary at 55.5. So now let's calculate the z-score of this left boundary, so that ultimately we can find the area in between. So the z-score of 54.5 is 54.5 minus the mean of 50 divided by the standard deviation of 5. So now we have 4.5 on top divided by 5, or 0.9. So now that we have the two z-scores, let's look those up in the table to find the two left areas. And then we'll subtract the two left areas from each other. So let's start with a z-score of 1.1. What's the left area? 0.8643. Okay, and then let's find the left area of the z-score of 0.9. 0.8. 8159. Okay, great. Okay, so now that we have those two left areas, we just subtract them from each other to get this area in between that we want. So let's go ahead and subtract them from each other. Okay, good. So this is the answer that we get from only this blue bell curve. Now we've ignored the underlying binomial probability distribution, aside from using that just to calculate the mean and standard deviation. But we're using only the blue bell curve, and we're finding the probability of this data point at 55, because we know that to find area using this continuous distribution requires finding area. And so for this single data point of 55 heads, we're going to assign it an area or a region in either direction of 0.5. So that's how we're getting the 54.5 on the left and the 55.5 on the right. And then we're finding the area around that data point of 55 by finding the z-scores, looking up the left areas and subtracting the left areas to find this area. And this area turns out to be 0.0484. That's an approximation from this blue bell curve, but how close is it to the actual answer? If we find the height of this bar, it turns out to be very close to the actual original answer. So this is an alternative way for us to find the same probability that we want for a binomial probability distribution. So right now you might be thinking, okay, that's great that using this complicated technique, we're able to get the same answer as before. But before, we got the answer very easily by using this formula. And the approximation seems like it's much more complicated, even though it's a good approximation. So why bother? So the answer to that is this is just to show you that it works, that you're getting similar answers. But the payoff comes when you're adding up multiple binomial probabilities and it's not feasible to do that. instead, it's much more feasible to find areas under bell curves instead. So for example, so instead of the previous question, where we found the probability of 55 heads out of 100 flips, let's now find the probability of at least 55 heads out of 100 flips. So what does at least mean? Just logically.
Last one?
No, at least actually means either, either equal to 55 or more, right? So we could have any number of heads, now not just 55, but either 55 heads or more than that. It could be 55 or 56 or 57 and so on, all the way up to possibly even all 100 flips or heads. So this is what originally we want to find. We have a probability with OR here, so which mathematical rule of past was that? That was the addition rule, great. So that means that you can separate this out into separate events and find the probabilities of each of those and then just add them together. So this would be the probability of 55 heads out of 100 flips. Plus the probability of 56 heads, plus 57 heads, and so on, all the way up through 100. But this would require you to add up all these probabilities from 55 up through 100. And how would you find each probability?
Same formula.
Yeah, we come from the same binomial probability formula that we talked about earlier. But this formula is pretty cumbersome to use. It's a long formula, and you have to apply it all these times from 55 to 100. So you have to apply it 46 times, going from 55 to 100. So this is not feasible to do. We have to add up all of these probabilities together. So, and visually, this is the same as us adding up the probabilities from 55 to 100, which is adding up the heights of these bars from 55 to 100. So that's what we're doing visually, but it's not feasible to do that with this original black binomial probability distribution. So instead, we're going to fit this bell curve to approximate the underlying binomial probability distribution, and then we're going to find the area or the probability using this new bell curve and find any areas that we want to approximate this probability instead. So instead of having to add up all these probabilities using the binomial probability formula, now we're going to use this blue bell curve we're going to look at the data point of 55, but now because we went from a original binomial distribution which was discrete to now a bell curve in blue which is continuous. The way that we find probabilities for continuous distributions is different and finding probabilities for discrete distributions. To find probabilities for continuous distributions, we're finding areas, versus for discrete distributions, we're adding up individual values. So now if you want to find the probability for a data point in a continuous distribution, you have to convert that data point into a region that you can find the area for. So that's what we did earlier, in the earlier example, where this data point 55 now has a region around it of 0.5 in either direction. So based on how we round numbers, 0.5 in either direction, 54.5 to 55.5. So this describes the one data point at 55. It's this region with this area. Now we want not only 55, but we want everything more than that as well. So that means that we're going to include the area to the right of that as well. So this reduces down the problem of, now we have this bell curve, what's the area to the right of this region whose edge is 54.5. So let's do that. So now we're going to approximate this answer with a very good approximation of finding this area here for this bell curve. And so this region that we're trying to find the area for, where's the edge of that? Yeah, very good. It's not at 55, but the edge was the left of that, which is 54.5. So we're going to use that to find the z-score.
So would we not just, we already have the region for that, we'll just
Right.
subtract one? And
Exactly. So that's our game plan, is to find the z-score 54.5, but in the earlier question, we already found that, right? So the z-score 54.5 ended up being 0.9. So now we're going to find the z-score for this, which is 0.9, and now we're going to find the total area to the right of that.
Which we did too.
Yeah, which we pretty much already did. So we found the left area, which is 0.8159. So that's the area to the left. What's the area to the right? Yeah, 1 minus this, which ends up being 0.1841. So this total area to the right here ends up being the same answer as if we had added up all these probabilities from 55 line. Any questions? Okay, so you notice that this right area we found, I just found the right area, and technically, we should have stopped at 100, but I found the total right area, and I didn't technically stop at 100, but I'm able to get away with that, and why is that?
So insignificant.
Yeah, very good. So this total area to the right of 100 is going to be so insignificant that it's going to add up to virtually 0. So that's why, if you wanted to be a stickler, then you could have found this region at 100 and just found this total area between 54.5 and 100. But this area to the right of 100 is going to be so insignificant that we can also just find the total right area and not lose much accuracy. Yeah.
So we have a really big number that uses the addition rule, we can just use central limit theorem.
Yeah, close. So let me basically specify what you said. So basically, when you find yourself adding up multiple binomial probabilities, then there's a shortcut. We can fit a bell curve on instead and find the relevant areas instead for the same probability. Any questions? Okay, so real quick, guys. So you see that when you add up multiple binomial probabilities, we have a shortcut to fit a bell curve onto it instead. So now let's talk about the assumptions of when we're able to do that. So there's only one quick assumption. And I'm gonna illustrate this with a counterexample. Let's say that you have a coin, but this time the coin is not fair. So you know that it's loaded, and this coin is unfair. But let's say that the coin is so unfair that you get heads every time you flip it. Let's say that it's a two-headed coin. So it's a two-headed coin, and you get heads every time you flip it. I don't know why you bother flipping it then. But let's say that you flip this coin 10 times. So this is a two-headed coin. And if you were to look at the graph or the distribution of the number of heads that you observe after flipping this coin 10 times, what would you expect the probability distribution to look like?
Just one
line, nothing else.
Yeah, very good. So, because when you flip the coin 10 times, you're gonna get 10 heads every time you flip it 10 times. So at 10 heads, you're gonna get a bar with a certain height that represents that the probability is 100%. And what about all the other values? Yeah, it's gonna be 0 probability, so you're gonna get heights of bars that are 0. So you're gonna get only one line here. So we said that most of the time, if you have a binomial probability distribution, it's gonna look like a bell curve. And that's why you could approximate a bell curve onto it. But in this case, does this look like a bell curve? Very good. So technically, this is a binomial probability distribution, but you cannot fit a bell curve onto this because you don't have enough mass on both sides of the mean here. So in some rare cases, you're not able to fit a bell curve onto a binomial probability distribution. So we want to be able to quantify those rare cases. So the way we quantify it is we say that you can only fit a bell curve onto a binomial probability distribution if NP is at least 5 and also NQ is at least 5. So in this example, let's see if the assumptions work. So what's NP in this example with the two-headed coin flipped 10 times? Yeah, and it's gonna be 10 because you're flipping the coin 10 times. And what's P?
2.
Yeah, P is the probability of success or heads. So that's gonna be 100%, that'll be 1. So it'll be 10 times 1, which is 10. So in this case, this assumption currently is met because 10 is at least 5. But what about the second assumption? N is gonna be 10. But what's Q, which is the probability of non-success or the probability of tails?
0.
Yeah, 0, very good. So that's the probability of tails, because this is a two-headed coin. So 0 is not at least 5, so this assumption fails. So this is going by n, so both assumptions need to be met. So because both are not met, this assumption fails, and that's why in this case you're not able to fit a bell curve onto the problem. And in this case, if you found yourself having to add up multiple binomial probabilities, then you would not be able to fit a bell curve onto this. You would have to actually add up the binomial probabilities. Okay, any questions, guys?